Hello everyone. In this video I'm going to go over the heteroskedasticity tests. The classical linear regression model assumes that the conditional variance of the error term conditioned on the set of regressors or x's is equal to 0 or is equal to a constant number. In this video we're going to violate this assumption by creating a model in which the error term would depend on one of the x's, or more specifically, the variance or the conditional variance of the error term conditioned on one of the x's is going to be linearly dependent on one of the x's here. So as x1 increases or decreases, it's going to affect the variance or the conditional variance of the error term. To do so, we're going to generate random variables. And the model that we have is y is equal to beta naught plus beta 1 x1 plus beta 2 x2, assuming that these coefficients are just taking 1 for simplicity. And an error term, and this error term is equal to a certain nonlinear function that depends on one of the x's. Let's make it x1. Each of the variables that we have in the model are normally distributed with mean 0 and standard deviation 5, or the variance is 25. We're going to set the seed, where the seed here is just a code to enable all of us to get the same set of random variables. We're going to set the observations to be large number of observations, 500. We're going to generate the x's by a certain format called double. You have different options like float, double, binary, and so on. We're going to generate x1 as being double with a normal mean 0, standard deviation 5, and the same thing for x2 and e. And the error term is the square root of the function we just mentioned here. So our model, we're going to generate our model y as a function of x1 and x2, and we can summarize and see what we've got. Of course, the first comments here are related to the memory, to just make sure that you have, let's say, 10 megabytes of memory. Set more off so that you don't get here the word more, so that you click on it and get more results. You just want to set this off so that once you run, you get all the results all at once. Here you don't have to click on more. And then this is just a comment related to how the graphs look like. So let's run the model up to here and see what we are going to get. So what we have is a set of observations as we asked Stata to create the 500 observations. X1, for example, has a mean or negative of 0.011 and so on. Standard deviation of this number has a certain minimum, has certain maximum. Everything here is just random, okay? And then x2 and then e, the error term, and then the y itself. Next, we're going to do the regression. So this regression is just the OLS regression, and we're going to regress y on x1 and x2. We got the results, okay, statistically significant based on the t, statistically significant based on the p, statistically significant based on the confidence interval, as it does not include the 0. So if it includes the 0, then we have statistical insignificant coefficient. Next, what we want to do is to see whether we can really see the heteroskedasticity problem of the error term. Is there any connection between x1 and the u, as we have already made it in the model? So to do so, let me skip this one for now, and I'm going to do the graphs. So the graphs here, we're going to graph each error term, or the absolute value, or you can do the square of the error term. You don't have to create the absolute. Like, for example, here I created the absolute value of the error term because I might have a negative, I might have it as a positive, but you can also create the square of it. You don't have to create the absolute, like different ways of doing it. We're going to create one graph of x1 with the absolute value of x2. Everything else here is related to the title, the scale, the thickness of the graph, like everything is kind of more about formatting. The part that you really need to focus on is this. We're going to get a scatter plot of the absolute value of the error term versus x1. The same thing for the next one. the absolute value of the error term versus x2. And to make our life easy, we're just going to combine the previous two graphs. So let's see this. We're going to run. Okay, so this is the combination of the two. So as you can see here, just look at the thick line. The thick line here is telling us that it's increasing at an increasing rate. The relationship between the absolute value of the error term and x1, and this is actually expected because we already have created this in our model using the simulated data. This one is, yes, it's increasing, but it's not as steep as in the case of x1. We might have some observations here, but it seems that these observations are not as important as the concentration of points here in this area, and that's why the line does not come all the way up. As we can tell from the graph, this one has heteroskedasticity, this one doesn't seem to have heteroskedasticity. Someone might say, but still I do have some increase in the line that is like, it's not zero by the end of the day. That's why we need to do like a test. So we need to perform a test to confirm what we see with our eyes. Like what you see with the graph is not the end. You need to do a statistical test. But what we can see by the graph, this is heteroskedasticity case, this is a homoskedasticity case. The line passes through a certain constant range of observations, but this one is increasing. So if we do the graphs, and the graphs can tell us that we have a heteroskedasticity issue, then we need to perform tests. There are different tests to do. We have what is called an M-test, and the M-test, as you can read in the green lines here, it's going to test, or it's going to perform multiple tests. It's going to perform a test on x1 separately, on x2 separately, and then for x1 and x2 jointly. I might have heteroskedasticity here, and I might have homoskedasticity here, but I would care also to know what about the joint heteroskedasticity in both x1 and x2. So let's run this part, and this part is about it's called estimate. It's like saying estimate heteroskedasticity test for x1 and x2, comma, M-test. And this one would give us the Bruch-Pageant test, and in this one is showing us a p-value for x1 saying, and remember all the time you need to remember that the null hypothesis is homoskedasticity, constant variance. There is a zero probability that x1 has constant variance. So we can say that we are rejecting the null hypothesis because it has a low probability, and we are accepting the alternative, or we are going to say that x1 has heteroskedasticity. What about this one? If we use the 1% significance level, then I'm going to say that there is a high probability of heteroskedasticity there is a high probability of constant variance in x2. In other words, we have homoskedasticity in x2 based on the 1% significance level. Of course, if you use the 5% significance level, you're going to say this is a low p-value. And in that case, you would say, okay, I might also experience heteroskedasticity or I also have heteroskedasticity in x2. That's why the simultaneous test is very important. The simultaneous test is just confirming the result that we got for x1 by saying that there is a zero probability of constant variance for both jointly. In other words, we have heteroskedasticity in x1 and x2 together. This is the M-test. There are different versions of the test. Okay, so the H-test that we just did, let's say you can also, let me just run this one, okay, and this one is showing us again the Bruch-Pageant test in fitted values of y. What does it tell us? There is heteroskedasticity in fitted values. It's very, very important to know that the H-test and the m-test assumes that the error term is equally normally distributed. Assumes that the error is normally distributed. If I want to break this assumption, and if I feel like the errors are not normally randomly distributed, then I have to add the option IID. So let me return this back here. If I add this option of IID, then now I'm telling Stata, estimate for me a heteroskedasticity test, assuming that the errors are not normally distributed. So we have different versions of this test. This one again, if the errors are not normally distributed, again, we have heteroskedasticity. We can have another version of the test by having x1 and x2 together, right? And this one again confirming that we have heteroskedasticity, or there is a zero probability of constant variance, so we have heteroskedasticity. We can also do it only on x1. And if I do it only on x1, there is a zero probability of constant variance in x1, so there is heteroskedasticity in x1. I can do it on x2 only and can see the result, and it's saying, okay, this is a very big number. There is a 33.13% probability that this variance is constant. In other words, it's a big number, right? It exceeds the 5% significance level, it exceeds the 10% significance level. It's just a big p-value. So this one just confirms that x2 is homoskedastic. Right? So those are different types of models. Just remember that anytime you're going to add IID, then you're just basically relaxing the assumption of normally distributed error or errors. Okay, and the last test I want to show you is called the information matrix test. This test actually performs three important tests together. So it performs a homoskedasticity test, a symmetry test, whether this distribution is symmetric or not around the mean, whether it has a kurtosis of coefficient 3. The normally distributed or the normal distribution, or a variable that is normally distributed, has a kurtosis of 3. What does that mean? It basically means that we have the extreme values are 3 standard deviations from the mean. If I have a bigger number than that, then it's not like you have a high kurtosis, so basically means that you have more extreme values than a standard normal distribution. If it is smaller than 3, then it's basically saying that the extreme values are less than a standard normal distribution. So anytime you're performing a test, you have to know what is the null hypothesis, because based on whatever you see on the null hypothesis, you will be able to explain the results. So let's perform the IM test. And the IM test is showing you the results here. Again, it's much easier to look at the p-value. The p-value of the first test is what? It's homoskedasticity. There is a zero probability of homoskedasticity, so it's telling me that this model is heteroskedasticity. I'm sorry, the second one, there is a high probability of symmetry. So in other words, the model is symmetric, which is good. Whatever you have on the left of the mean is symmetric to whatever you have in terms of a distribution towards the right of the mean. The last one, whether we have a kurtosis of 3, right, because this is the null hypothesis here, so it's telling us that we're rejecting the null and kurtosis is non-normal. So based on this test, we can come to this conclusion. The model is heteroskedastic, symmetric, but kurtosis is non-normal. Okay, so again, the good thing about simulating dataset is that you're creating a problem in your model, and you already know that you have this problem, but you want to see in the results and how the tests are going to show you the results that you already know. Later on, we're going to apply these tests to datasets that we do not know whether it has heteroskedasticity or not. The final thing I want to mention is, knowing that we have a heteroskedasticity in the model, how can I deal with it? You basically will need to use a standard error, which is called a robust standard error. So you can write it VCE robust, or you can actually remove this part and write just robust, or you can remove this part and write the letter R. All of them are going to give you exactly the same result. So let me run the two together, which is the regular model and the one with robust standard error. So this is the regular model that we did perform at the beginning of this video. Okay, what we see here is just the regular standard error. If I notice that I have one of the variables has heteroskedasticity, then I have to deal with this problem by adding a robust option, and this would compute for me the robust standard error, which is this one. So the robust standard, as you can see, is different between these two tables, right? And it's very, very, very important to notice that our coefficients are exactly the same, because heteroskedasticity has nothing to do with the computation of our coefficients. Heteroskedasticity is all about the variance problem, or anything computed based on the variance, like the standard error, standard deviation. The t-statistic is going to be different, the p-value is going to be different. Of course, here it's already 0, so like slight change in the t-statistic will not affect too much the 0.000. The confidence intervals would be different, and so on. So T, P, confidence intervals all depend on the standard error, which has changed from here to here, and accordingly everything else is going also to change. All right, so I'm going to stop here, and later on I'm going to show you another video on how to use simulated data to detect other types of econometric problems.